Today we'll present to you teachable reinforcement learning via advice distillation. From birth, humans are taught with a diverse set of feedback forms. As babies, we learn from forms which are simple but easy to understand, such as smiles from our parents. As we grow, our parents incorporate more complex instruction forms like demonstrations of tasks. As our range of communication grows, we add in a rich array of other forms, including verbal corrections and instructions, text and diagrams, numeric metrics, symbols, and more. In contrast, when we teach tasks to robots, we're able to give simple feedback forms like rewards, or intermediate forms like demonstrations, but we still lack the rich, expressive set of communication channels which make it easy to teach humans. If we can develop expressive and convenient communication forms to supervise agents, then humans real-world tasks and may become an essential part of the way we teach our robots. Researchers have developed many ways to supervise our agents. The most popular forms face a trade-off between information density and convenience. The supervision forms which are easy for the human to provide, such as binary preferences and sparse rewards, contain very few bits of information. On the other hand, more complex supervision forms, such as dense rewards, may be time-consuming to provide, and demonstrations aren't possible at all for some tasks. We'd like to expand this set of supervision forms to include feedback forms which perform fairly well on both axes, such as corrections, subgoals, and language. Here, we run into the problem of grounding. These communication forms are easy for the human to provide, but challenging for the agent to understand. Our insight is that we can use lower-level, easier supervision forms to help us ground more complex supervision forms. We can formalize our problem setup by modifying the multitask MDP problem formulation, in which the goal is to learn a policy which conditions on the current state and task tau. At training time only, we introduce a human teacher who can provide the agent with contextual prescriptive advice C. This advice can take arbitrary forms, such as corrections or subgoals. We call this a Coaching Augmented MDP, or CAMDP. Two challenges present themselves in this setting. The first is how to best make use of the teacher's coaching. The second is how to make the agent succeed at test time when the teacher is removed and the agent has to execute the task without assistance. In this paper, we present one method for answering these questions and solving CAMDPs. At a high level, we use coaching by learning policies which condition on the teacher's advice. Then we distill these policies into an advice-free policy. We'll use a learning task in the ant maze environment to illustrate our method. In this environment, exploration is too difficult for an agent to learn effectively with sparse rewards. Demonstrations aren't an option at all, since the human can't control the high-dimensional action space. While the agent can learn from dense rewards, this process isn't sample efficient. To make this learning easier, we'll start out with a simpler maze. We'll also give the agent a teacher, who will provide advice which will be concatenated into the agent's observation. We'll start with an advice form which is easy for the agent to understand. At each time step, the teacher says what vector direction the ant should be traveling in. After the agent takes an action, the teacher also provides a dense reward, penalizing the agent for following coaching incorrectly. Since this reward is dense, we can quickly train an agent which can be coached using direction advice to reach any point in the maze. In this paper, we train using PPO, although any RL algorithm could be used. At the end of the process, we've trained a policy which conditions on the simplest form of coaching. By rolling out this policy with human advice, we can now coach the agent through new mazes on the first try, including mazes which are more complex than those seen in training. The human doesn't need to provide any more rewards during this stage. Effectively, the human now has the ability to produce expert demonstrations while only needing to provide a low-dimensional, convenient piece of advice at each time step. The issue here is that we would like to succeed on test tasks without the human constantly being present. To do this, we first roll out the advice conditional policy and create a buffer of expert trajectories. Then, we treat these as ground truth and use behavioral cloning to train an advice-free agent. We call this process distillation. With distillation, we're able to leverage advice, but ultimately perform well without it. We're still missing one piece of the puzzle. At the moment, a human needs to provide advice for every time step which goes into our buffer, and this can be inefficient. Instead, we like to learn to use higher level advice. We do this through advice relabeling. To do this, we roll out the low-level advice conditional policy to generate successful trajectories. Later, the human relabels each trajectory with a different type of higher-level advice, in this case, waypoint. We use these relabeled trajectories as ground truth labels to train an advice conditional policy for the higher-level advice through behavioral cloning. We call this process bootstrapping. Since reaching a waypoint is a simpler task than solving an entire maze, we can bootstrap a waypoint conditional policy much more efficiently than learning to solve the entire task. We also need to perform this advice grounding process only once, and then we can use it in each new test maze. Finally, we have a viable pipeline. Quickly use RL to ground low-level advice, then use low-level advice to ground high-level advice. With a human only providing high-level advice, we can efficiently collect enough data to distill an advice-free policy. This bootstrapping process doesn't only need to happen once. Instead, we can apply it repeatedly, going from simple but easy to ground advice like directions or actions, and moving to gradually richer advice types, including corrections, subgoals, and language. One extension to this approach is to replace in the loop advice during the distillation phase with off-policy advice. Rather than rolling out the advice conditional policy, we roll out the advice-free policy. Later, the human relabels the trajectory at several points with high-level advice, coaching the agent what to do next in the trajectory. Next, we run these labeled trajectories through the advice conditional policy to obtain an optimal action for each time step. We treat these actions as ground truth and use them to update the advice-free policy through behavioral cloning. This off-policy approach is analogous to performing Dagger with high-level advice. Let's see how our approach compares to other popular methods. Our distillation phase is very similar to behavioral cloning and Dagger, but rather than providing an action at every time step, the human just has to provide occasional high-level advice. Unlike a pure multitask RL setup, we only use RL to ground the lowest level advice form, after which we use more sample-efficient behavioral cloning for the rest of training. Finally, our method differs from instruction following in that we can learn from arbitrary prescriptive advice, not just instructions, and that the advice conditional policy is only an intermediate which helps us learn an advice-free policy. Our method is only useful when certain conditions are satisfied. First, we need to be learning a set of tasks with shared structure, or a single task with many configurations or repeated steps, so that the upfront costs of grounding advice are offset by the improvement in learning speed on the test tasks or configurations. Second, the human needs to know what a successful policy looks like. Even if the human can't physically generate optimal performance, they need to be able to coach the agent to success in the task. Next, we note that since our method can be seen as a more efficient way of obtaining expert demos, applying our approach only makes sense when there is not already a large dataset of expert demonstrations. And finally, the tasks must involve subtasks, skills, or decisions, which can be made easier through advice. Next, we'll show some examples of how our method performs on tasks like these. We tested our method in a few environments, including Baby AI and Ant Maze. In Ant Maze, we used per time step directions, cardinal directions, and waypoints as advice. In Baby AI, coaching ranged from per time step action advice to higher level coordinate corrections and semantic subgoals. For our initial experiments in both environments, we used a scripted teacher rather than a real human. In both environments, we trained on a set of procedurally generated easy training tasks. We grounded the easiest form of advice through RL, then did bootstrapping to learn the other forms. Next, we rolled these advice conditional policies out in a test environment. For Baby AI, we use a single static maze task in which the agent must move a pair of matching colored objects near each other. In the Ant Maze environment, we test on larger mazes than those seen in training. Finally, we distilled from the conditional policy for each advice form to an advice-free policy. The plots shown display success on the y-axis, plotted against the number of units of human supervision given in this particular environment on the x-axis. Each supervision piece, a piece of advice or a reward, counts as 1 unit. We see that in these environments, RL completely fails to learn in a sample-efficient way. We also see that runs which incorporate higher level advice, shown in blue, tended to perform better than those using low level advice in red. Our method does fail sometimes. We see this in the largest ant maze 3, where no method gets more than 10% success. To better evaluate whether our method speeds up teaching, we tested the efficiency of the distillation phase with real humans on one baby AI environment and 2 ant maze environments. In both cases, we started with the advice conditional policies which we pre-trained with a scripted teacher. Human volunteers for each condition were given a fixed amount of time to provide as much feedback to the agent as possible. In baby AI, where providing demonstrations is extremely easy, we found we performed comparably to a behavioral cloning baseline. In the ant environment, where demonstrations aren't possible due to the high-dimensional action space, we compared against providing a shape-dense reward computed by our scripted maze solver. Our method, trained on 30 minutes of human data, outperforms RL until RL is given thousands of times more supervision. There are multiple limitations to the method we've presented so far. One limitation of our method is that it relies on accurate grounding of advice, which may not happen in the presence of other correlated environment features. If advice is grounded poorly, the agent may get stuck when it's being coached through out-of-distribution situations. Another limitation is the sample inefficiency of the grounding phase, which might be improved somewhat by incorporating unsupervised pre-training. Finally, our evaluation of our metric could be improved by developing a cost of supervision metric for scripted teachers, which better matches real human effort, or carrying out more extensive real human experiments. To recap, our paper takes one step closer to our vision of supervising agents with the same rich communication available to humans. We aim to solve this CAMDP problem by first learning a set of advice conditional policies and distilling them into an advice-free policy. Our method reduces supervision costs in both simulated and real human experiments. Please check out our website for more details.